It's always a pleasure to come here. So I've done this presentation a couple of times, or some very similar version of, and so sorry for the repeat for the people who have already been in there. But so microinverters, it's a big subject. When my friend and I started Enphase in 2006, microinverters were not a new concept. People had actually already released product in the late 90s doing microinverters, and the problem it was actually a failure back then because the technology was not quite ready to supplant string inverters or regular inverters. When we started this in 2006, I thought it would be a really difficult project, but very interesting as well. Interesting it has been, it still is. Difficult was a major understatement. It's been far harder than I ever thought it would be. So let's start. So what is it? Microinverter is a part of a PV grid-tied system. So we've never been connected to, we've rarely been connected to a off-grid system. Our output product is basically energy in the form of current that we inject on the grid. Whether it's in the grid directly or within the house wiring, it's still the same result, is we inject current onto the voltage which is already there. If the voltage is not there, we're actually prohibited by standards to export energy. Okay, so if you want a microinverter to work when there is no provider, it won't work. It's prohibited to. So the system is a series of microinverters. You see one here mounted on a rack where the module, onto which the module is mounted. We have a gateway which is plugged in inside the house and is connected via power line communication to the series of inverters. And lastly, we have a web server that we host where all the gateways send data on a 5-minute basis to our server. So we received, as an example, we receive right now about 100 gigabytes of data a day into our server. So it's major data. So where does energy come from? It comes from a module. So a single photovoltaic module, typically right now in the 250 watt range. We harvest the energy, we transform it into AC current, and we inject the current to the grid. The unit monitors the module, voltage, current, so on and so forth, and itself. So we know what temperature it's operating at, what the voltage of the grid is, what the frequency. We can even download the actual waveform of the grid if we want to. And as I said before, it won't work if the grid is gone. Okay? We have sold about over 3 million units, and we are the first inverter vendor right now for residential market in the United States. So why do we do this? Well, it's productive. It basically harvests more energy than a string inverter system because we optimize each module independently from the other. And while regular systems, in regular inverters, all the modules are put in series parallel combination, and then you have a single MPPT, maximum power point tracking, that attempts to extract the maximum amount of energy out of the array and gets it. The problem is, of course, that optimum is not the sum of all the local optima, right? So because we're distributed, we can extract quite a bit more energy than any string inverters could do. It's also reliable because we have no single point of failure. If one of the units goes bad for whatever reason, we just impact that module, not the entire system. A regular inverter, when it goes down, the whole system goes down. So clearly, it's a superior solution as far as the availability of the system. Something which is interesting to understand as well is that the power electronics in there is operating a much reduced power level than a regular large inverter. You know, if you have a megawatt inverter, you'll be dissipating 30 kilowatts into the inverter. It's a big amount of power, and the box is big, but it's not that big, which means that the density of DC power dissipation is very high. In our box, we dissipate 5 watts, 6 watts, 7 watts in a small box, but it's much easier to do. And we don't have to have any kind of air cooling with forced air, or water cooling like big inverters have to have. So it's also much simpler as far as power dissipation. Another point is that the devices that we're operating are much closer to the surface of the box. So the path from the chips that we use to the air is much, much shorter than on a large inverter, which makes things a lot easier. As far as operating temperature, as an example, I believe that we operate cooler at the maximum ambient temperature of the unit than a regular inverter at the 25C, because we have it's so much easier job to dissipate energy. Smart, we have full system monitoring and analysis, so we can figure out what each module is doing, what's the impact of, for instance, shading on one module will be. We can figure out if there are any problem with the grid voltage. All this analysis are possible because we have all this data available. We don't need to do string calculation. On a string inverter, you have to figure out how many modules you put in series and how many string of series modules you put in parallel. It's not required. It's very simple, one by one. Anybody can do it. I can do it, so anybody can do it. All the wiring is in AC versus a whole bunch of DC wiring. And I don't know if you've ever done this, but if you put even 3 modules in series and you make a short and you try to open the connector, you basically get a fire. Because any bad contact in the DC current loop will create an arc which will reach 4,000 Kelvin pretty easily. So in this case, we only have one module connected in DC to an inverter running at 20, 30 volt. You simply cannot get an arc with that system. And on the AC side, of course, we're replacing DC wiring versus AC wiring. Man, AC wiring is a very well-known problem, and because of the AC nature of this, the current zeroes out, 120 times per second. So arcs tend to extinguish very, very fast. So it's much safer for that point of view. And of course, we lower installation time because it's a very easy system to install. It's pre-wired basically, and it takes much less time per module than a regular system. So safe, we already talked about high voltage DC and the fact that there's no power source, little power source present when AC is shut down. When you have a fire in a building, the fire department, they're not very happy with solar because they know that on a regular solar system, there's no way to shut it down. You can interrupt, if you go on the roof, you have sometimes a DC disconnect, you can interrupt that, but the first thing that firemen do when they go on a building is cut a hole in the roof with a chainsaw, and they don't know if they're going through conduits or high voltage DC or anything. So for that matter, when there is indeed a problem, a fire in a building, what they do is that the fire department takes the whole meter out, and there is no AC power anywhere, and the only thing left are distributed 20 volts, which are not lethal or dangerous. So those are key selling point, I would say, for microinverters. So let's look at the pieces of the puzzle. We're connected to PV module. It's not, in the industry, it's not called a panel, by the way, it's called a module, because panels are for AC breakers. So, people in the know use module instead of panel. The function of those is obviously to translate photons into electrons. And multiple technologies are usable for this. By far, the most common one today are silicon-based products such as crystalline, polycrystalline, and monocrystalline silicon modules. Of course, those materials are available: cadmium telluride, SIGs, even gas. But we've, in the 2008-9 timeframes, there was a huge momentum towards thin film, which seems to have stopped, basically, as far as we can tell, on the marketplace. We never, basically, almost never connect any module, any of our inverters to a thin film inverter. Vast majority of the modules out there right now are passive, meaning just a bunch of diodes in series. Some modules have concentration and require the right angle towards the sun, right? Okay. So more on the silicon module. It's cell-based. Cell is either 125 millimeter, which is actually going away right now, or 156 millimeter, which is the vast majority of the market. Cells are arranged in series, anywhere from actually 42 in Japan all the way to 96 cells. Rule of thumb is that a cell will provide about half a volt at full irradiance and at 25 C. So if you have 72 cell module, rule of thumb is going to be running about 36 volts at 25 C cell temperature. Typical module efficiencies are in the 12 to 20% range. And they're going higher, but the rate of improvement of efficiency is about 3% per year. Not 3% of efficiency point, but 3% year over year on, relative to the previous efficiency. That's what I've seen over the last 20, 30 years. And when you look at the graphs from NREL, for instance, that ticker line comes about there, and it's pretty steady. The output power, of course, depends on the irradiance. So 1,000 watt per square meter would be a full sun, pretty much, and that's where you usually that is what the module is rated for. So if you have a 250 watt module rated module, you'll put out 250 watt at 1,000 watt per square meter incoming irradiance. Of course, all that depends on the angle of the rays coming in, the shading, soiling, and matching of the cell within a module will affect production. So big item there is the output power depends mostly on the first order depend on, of course, on irradiance, but on second order depends as well on cell temperature. So typical modules test at 25 C cell temperature. But they do get really hot, so it's not uncommon for a cell to reach 75 C in the middle of the day in summer. And because the rating of the power production versus temperature is about 0.4% per degree C, you could have a very significant degradation when the cells reach 75 C. So 0.4% per degree C, let's say a cell is 75 C, it's rated at 25, so a 50 C rise, that's 20% degradation in output power. The output power is reduced mostly because the voltage is reduced, as any diodes forward voltage will do. Okay? So what's important when you try to match a module and an inverter? Well, number of cells and size is a big thing. Power rating and the voltage and current characteristics needs to be considered. So as an example, I have a 240 watt maximum power point modules with a 30 volt VMP and 8 amps IMP, which is maximum power current. Those are very typical characteristic for a 60 cell silicon module. And that's what we design our inverter to work with. Okay? Such a module would be about 1 meter by 1.6 meter by 40 millimeter thick. That would be standard dimension, or right about for this type of module. And the temp codes would be about, power would be minus 0.4% per degree C, as I said in the previous slide. Those are all typical characteristic of module you can find on the marketplace right now. Okay. So what is the IV curve of such a module? It will look like this. On the left-hand side, you have the blue line is 1,000 watt per square meter. At 0 volt, you'll get the ISC of the module, the short circuit current. In this case, about 8.5 amps. When you reach 36 volts, you get to 8 amps, which happens to be the maximum power point. And then when the voltage increases, the current drops all the way to, the previous point was about 30 volts. This VOC on this one, output circuit voltage is 36 volts. When the irradiance drops, the whole curve is shifted down. So 200 watt per square meter, we have only 20% of the curve we had before. It's all shifted down to 20% of it. And on the right-hand side, you have the power now versus voltage, and you see a very nice maximum power point at about 30 volts. Okay, so those are very standard, typical characteristic of a module.